Good afternoon, everyone. My name is Rutger Marquart. I'm a PhD student and part of the Polar Engineering Research Group. I'd like to introduce my PhD project, Computational Modeling of Ice Flow Dynamics in the Antarctic Marginal Ice Zone, by using 5 headers, starting with the main objective. So the main objective of my PhD is to develop a small-scale model in the computational fluid dynamics software OpenFOAM, which describes the interaction between ice flows and ocean waves, considering interstitial grease ice subjected to simplified wind, ocean current and wave forcing. The main reason for this research is the lack of data of atmosphere-ocean physical processes on a smaller scale within the Antarctic Marginal Ice Zone. The main equations in my model are shown in the second box, methodology. The momentum equation describes the motion of sea ice and the constitutive equations describe the material behavior of the two ice materials I distinguish, which relate the deformation and the stress of both ice flows and grease ice. Ice flows behave like a solid and grease ice behaves like a viscous fluid. I consider a realistic sea ice layout shown in the bottom left figure in the methodology box, with in red the ice flows and in blue the interstitial grease ice. The ocean wave forcing, shown on the right hand side, consists of two components. The Froth-Krylov force acting only at the circumference of the ice flows, which comes from the pressure gradient due to the waves, indicated by P and P plus dP. The second component, indicated by tau SD, represents the skin drag, acting at the bottom of both ice flows and grease ice. In the third box, I show you preliminary results of a realistic sea ice layout subjected to a wave period of 12 seconds. The main variables in the small-scale model are shown, which are the velocity, stress, grease ice strain rate and grease ice viscosity. As you can see, results are detailed, which means that we can map, for example, ice flow collisions. Also, we can have a close look at the interface between ice flows and grease ice, where a significant increase in strain rate can be found. This results in a lower viscosity at the interface. The calibration of the model will be done by using imaging data obtained from the Antarctic during the winter cruise in 2017. Looking at a consecutive number of photos processed in MATLAB, we can find the position of each ice flow, which we can compare to simulation results obtained in OpenFOAM. Then, last but not least, future work, which includes the improvement of several components in the model, mainly improved constitutive equations to allow for more realistic material laws to take into account, for example, inelastic ice flow collisions and ridging. Also, a more realistic implementation of oceanic conditions to allow for wave dissipation. Lastly, we would like to find upscaling relations to link the small-scale model to existing large-scale models. Thank you for your attention.